Hello everyone, my name is Gurjeet Singh. Today I am going to present a topic, a case study in optical character recognition, specifically towards the license plate detection. So let's go towards the problem statement. It is important to automatically detect the license plate number for the law enforcement authorities, and this is specifically for the fast moving vehicles. So in this project, given a license plate image, the developed model extract and predicts the text information via optical character recognition technology. Here I have used the convolutional neural network, recurrent neural network, and GRU units in that, and tried a various dropout scenarios like where should I place a dropout, how should I place a dropout, and how much should I drop out. These kinds of layers I have used, and various other functions I have implemented. I have used here Keras, TensorFlows, and Jupyter Notebook. And the background of this problem is the automatic license plate recognition was developed in 1971 by the Police Scientific Development Branch in UK. ANPR is basically currently used in many areas from the speed enforcement to tool collection to management of parking lots. Now the optical character recognition using the deep learning is now being tried in automatic license plate recognition space. So in this project, the description of the technologies I have used are TensorFlow, which is an open source software library for the machine learning and deep learning. I've used convolutional neural network, which are the deep neural network, as we can see in this picture here. And I have used the Keras, which is a little bit higher level library, or which is working on the TensorFlow, and TensorFlow is being used as a backend. And I have used recurrent neural network where the output of one of the unit goes to the second unit, and the memory being passed or used from the past. And here I have used GRU specifically, but LSTM is also available. And this model training was performed on the Amazon AWS using the P2X large instances, and where I have used NVIDIA Tesla GPU K80 GPU for the fast compute so that I can train my model fast. And you for transferring all my files, the data from my computer to the AWS, I have used FileZilla. And if I have to transfer back from the AWS to my local machine, I have used the same FileZilla. And this was done in the Python 3.6 on the Anaconda 5.1. And there are some other libraries like Matplotlib, which are for the graphicking, and the NumPy, it tools, and OpenCV for the images. And here I'm going to discuss about the data generation and my description of my data. So there's a website, Supervisely, which I use to generate 10,000 images of license plate, which are the fake images. And what I did is I created an project in the website, and I loaded their one of the data set from their data set library, and then I basically generated some images around 10,000, and these are the license plate images. And this website has the capability to annotate those images. So for the annotation, I wanted to have the annotation in the JSON file. So there was a script there which I ran to for the data transformation to generate my annotation. So we can see on this right side the annotated data here on the JSON file, and the IMG is for the images which are stored in the PNG format. The JSON file data we can see here has a description, which is the license plate number. The tags are here, which is the test or the training, and what is the size of the image, the height and width of it. And here we can see the PNG files. The images of the license plate are here for, and I am demonstrating a particular license plate over here. And now we come to the overview of the configuration or the setup. I've used Amazon AWS, specifically deep learning AMI with source code CUDA 9 machine for my all my training of my data. And I have used particularly GPU compute here, P2X large. And the hardware configuration is around like 11.75 ECU. One ECU is around like 1.2 gigahertz, the 2007 Xenon processor kind of capability. And I've used 61 gigabytes of memory and hard drive of 50 gigabyte SSD solid state drive. And here's an overview of the FileZilla software which I use to transfer my data. So once it is connected, I can connect it to the host, and then host means AWS, and then I can transfer my file to the host from my local machine, which is over here to the right side to the AWS. Now comes to the code highlights. In my code, I have used various functions and I implemented an image data extractor class under which I'm trying to go to a particular location where the images are capped, where the annotated JSON files are capped. So this class has various other methods implemented in that. So one of the method is process data, which we can see here, where I'm taking an image of some height and width and reading that image and then converting that image to a grayscale, particular width and the height. Here I'm using 128 by 64. Once it is resized, then I am dividing by 255 to basically normalize that image. And in this project, I'm using CTC loss. CTC loss is for the character alignment purpose, which is very important because we want to make sure our characters are like when we are training our RNN, so we are going in a particular sequence from left to right. So that means our width of the image is a sequence from left to right and then right to left. And this is the training of the model. Like what why I've created a function over here. I've used if you can see the convolution filters of like 16 filters in the beginning, kernel size of 3 by 3 filter size I have used. And then I have used the image data format of channel first. That means the first dimensional of the matrix of the array will be the channels here. And the batch size is 32. And there is a downsampling factor to reduce the size of the image I have used. And then you can see that I'm calling the image data extractor function, where I'm passing my image width, height, and the batch size. And I'm basically then getting the method of that class uh, process data to basically standardize my data. And I'm doing the same thing for the validation also. And then if you see that I'm taking the input data, my first layer, then the convolution layer I'm using, where I'm using ReLU activation, and then I'm having a max pooling. And in the second, after that, I'm using another convolution layer, and then I am using a second max pooling function after that. And then I'm trying to have a dropout layer of dropping zero point 0.1 or 10% of the nodes. And then after this, I'm reshaping the data for the CNN to input to the RNN model, RNN layer. So here, after doing that, I'm passing it to the dense layer to have the data in a particular dimensions. And then I'm implementing a bi-directional GRUs. So in this, I'm implementing a two GRU units one by one, and then I'm trying to merge both of these units together. And then I'm doing the backward GRU or the right to left direction, I would say, or backward. And then I'm again having a dense layer in the end. And after the dense layer, we are having the activation function, softmax function. Then we are getting a prediction out of it. So here I'm also using, as I told, that CTC loss, and then I'm using a SGD as a optimizer. And it may be possible during the back propagation that the gradient might explode. So I'm using a clip norm to basically clip off some exploding gradients. And this is about the dropout layer, like where should we have the dropout layer, what location the dropout layer should be implemented, how many dropout layers should be implemented. So I tried to implement the dropout layer after like two dropout layer after the convolution max pooling with 90% dropout, and then just one dropout after the second convolution layer max pooling, which also with the 90% dropout. Then I have two dropout after each convolution layer max pooling with 10% dropout, and here I achieved a pretty low validation loss. And then I also tried to just have one dropout after the dense layer with just 10% dropout. Then I implemented three dropout layers after each convolution layer max pooling and after first dense layer with 10% dropout. Then I had four dropout layers. But in case of like two dropout after the convolution layer max pooling with 10% dropout, I was able to achieve the minimum validation loss. So this is the best model I had, and this is my model architecture. So we have an input here of 128 by 64. Then we have a convolution layer, then max pooling layer, and then I have implemented a dropout layer, and then second convolution layer, and then the max pooling layer again. So the image size has been reduced, and we have like 16 features by 32 by 16 by 16, and then we have a second dropout. Then we have done some reshaping, then it passed to the dense layer, and then it is passing through the RN and GRU units. So they are like two GRE units, two layers we have used here. And then we are merging those layers, and then we are having us the third and the fourth GRU unit. But basically, they because it's a bidirectional unit, so it's the same unit. Then we are again having the concatenation, then dense layer, then in the end we are having a softmax activation to get to our output. So this is the code for generating the output. So here it is showing that we are loading the data in our image data extractor and then processing the data, and then you also want to see the activation map. So we are getting the layer output of the softmax, and the next function is basically is looping to plot the different predictions. So this is the demonstration of my result. We can see on the left the images of the license plate and the true character which is written here and the predicted character. We can see that it is perfectly matching. On the right side, we can see the activation map. It is showing that what character is being activated and at what particular feature, what particular place in the map on this 2D grid. And we can see the same thing for the second image. So it looks like it's nicely matched everything, and it looks pretty good. Now we summarize what are the lessons we have learned, what are the pros and cons. Summary and the lesson learned that we have demonstrated the CNN and the RNN technology together for detecting the character on the license plate image. Using these two technologies, we were able to achieve the high performance on the prediction. Here we have used the bidirectional RNN to help to relate to the sequence of the license plate. And we have also learned like how to use the dropout layer to avoid the overfitting and how much dropout to use and what is the location of the dropout layer should be best suited in the model. The cons in this project was that there was some hardware limitation because training a single model using the GPU took around 45 minutes. And Keras also is not do not have low level functions, so Keras backend was used here. And in the future work, like I would like to try this project by placing this license plate anywhere in the pitch image and trying to find that license plate and do the OCR on that. And also I would like to try the colored version of the license plate for this for the next version of this project. These are my references, and I especially give acknowledgement to Maxim, who is from the supervisory, from where we uh, able to generate the data. Thank you, everyone. Thank you.